Okay, for today's class, we're going to talk about how to use mix C and assembly programming, and we will give a simple example. Let's say if you are going to use assembly to implement the I2C library, and how do you do this, and how do you interface this with C language that they could use. So the agenda this evening is first we will see if you are using AVR GCC toolchain. So how does it support for mixed programming? So if you have multiple files, some of them assembly, some of C, some of C++, and how in this toolchain, what kind of configuration you need to use for that. And then we will talk about anything that when you mix program languages and then you deliver a project using multiple languages to generate the binary. There are three aspects for this, actually four. The first one is how does the parameters in one language, defined in one language, be seen by the statements in another language source code. That's variable visibility. So the other one is a function that's and the routines defined in one language source file. How could they be used by the source file of another language? The third one is because for one of the language, in this case is assembly, and assembly needs to have we need to have some presumption about how the registers are preserved or used during function calls. How is AVR GCC protocol to deal with register usage? And the last one is when we are passing parameters, because in assembly there's no symbolized parameters. So everything is basically need to give a fixed position of where the parameter is stored. So we also need to know what is the protocol when we use the AVR GCC toolchain to pass parameters. And then we will be talking about the 24LC256 EEPROM. And then if we need to design a project that we need to get our own customized EEPROM access routine using assembly language, how do we do that? Which is also very useful because if you are using a customized hardware that you need to map low-level assembly language to manipulate this hardware into a library, then you will need to write that in assembly language, and then you need to pack it into a C library to use. So you are pretty much writing a small driver, software-wise, that's the C program could use. That's basic agenda for today. And before that, we need to understand, first of all, everything eventually translated to machine code. So in this case, everything is actually translated to the machine code that has one-to-one mapping to assembly. So in this case, it's actually simple. We are talking about using a high-level language, which is AVR GCC C, embedded C, to map it to another language, which is assembly, and then mix it with some other assembly, which is easy. But in real life, you also have cases that you may need to mix and use two high-level languages. For example, you have in the Android framework, you're pretty much programming Java for the apps. However, the Android framework is basically built on top of Linux. Then in this case, all the native applications on Linux, they actually runs, they were mostly written in C or C++. So in this case, you basically need to, especially when you're writing a program, program that traverse the vertical layers from application to, let's say, driver to some low-level functionalities. In this case, you need to mix and use the Java language and the C language. And you do need to understand how these two languages will eventually talk to each other. And that's, of course, you always need some conduits to do this. And in the C and assembly case, the conduit is a compiler. So the compiler needs to actually understand the assembly language, and then it will, when it compiles the C source file, which has directives to mention some other references in assembly language, the compiler needs to understand this and generate assemblies as needed. But when you mix and use two high-level languages, the contour itself is a pretty complex entity. So for example, on the Android framework, all you need to have, you do need to have a virtual machine which translates the Java bytecode into machine code, because the Java compiler does not even generate machine code, right? So, and then once you generate that one, and then you need to have some unassembly process, or you use that machine code to generate assembly equivalent language, and then use this to map with C language. So at the last stage of the Java C mix and use, then it's basically very similar to what we are going to talk about tonight. So that is basically assembly language, assembly generated by the Java source converted by the virtual machine to bytecode, and bytecode convert into assembly, and then assembly gets mixed and used with the C language as a native layer. So that's basically one example of high-level language mix and use. So there are other, for example, you are using Python, and then in Python, then scripts you are calling C libraries. So there are also protocols to that. So we need to think about two aspects, which I really would like to emphasize. So when you are doing cross-language programming, there are two stages. One is static. That's when the software tool tries to understand your language and map it into something intermediate that could be understood by each other. So that's done by the compiler, or you see the interpreter in the scripting language case like Python. So that's a static stage. And then at the dynamic stage, then you do need something that can use the binaries generated by both language, and then combine them together. In the Java and the C language case, that's basically the virtual machine. So the virtual machine will dynamically convert your Java source code, generated bytecode, into assembly, and then this one needs to, so you always need support from both sides, at the two phases, one static, one dynamic. So that's basically, it's the 30,000 feet view of mixed language programming, and then we will give some solid examples. Is everyone following? Any questions so far? Okay. So there is application nodes provided by Atmel. So that's application node 1886. So if you go to the Atmel website, you download that one. It will talk about how the compiler is expected when you are mixing and use source code written in different languages. So that's a comprehensive reference. And along with time, that reference might also change, because code vision AVR GCC, it actually evolves with the GCC, and the GCC version keeps changing. So if in your future engineering effort doing this, I would encourage you to always check the latest application notes with regard to mixed programming. And in our not code vision AVR, but AVR GCC setting, the project, you may have already noticed that the project, when you click the new file, it does allow you to generate a new file that in C language, in C++ language, and in assembly. Of course, when you're using C language, it also comes from header files, which is basically facilitate use. And we're not going to, there's another application note actually, talk about when you're using C++ language, how is the code vision AVR GCC toolchain, how is AVR GCC toolchain handling this? But that's out of the scope of today's lecture. And the way the AVR GCC toolchain recognize what the file is by looking at its suffix. So if it is .c or .cpp, we understand this is a C or C++ file. If it is .asm or .s, we understand this is assembly file. And it will automatically use the assembler to handle this file. And header file and the inc file are basically that's the definition files for C language and assembly language. And this one will be done by the AVI-GTC preprocessor. So if you use a C file, but if you give it a wrong extension, then you will find the studio could not actually compile your program. So that's basically how that's a simple way to understand what kind of source file that is. And then the first matter that we need to address is the in both assembly and the C language, especially in C language, you already symbolized the variables. So then you have a variable, the storage location of the variable, you actually don't know. You don't need to know where it is. It's always come with a symbol that's a variable name. But then the issue comes up is when you are using assembly language to access such kind of variable, assembly language will only understand the location, right? The location could be the register name, it could be the memory location, or it could be I/O port. So in this case, the assembly language needs to know where is this symbol stored. How could I map this symbol to a concrete location? So we already see that when you are starting a AVI-GTC project and then you use compiler to do that, and in the listing file, you will see it already became assembly file. But the thing is, when we have multiple assembly files, you still need to know in another assembly file how do you find the storage location mapped to a symbol. So there's some protocols to that. The protocol is like this. So if the C variable needs to be seen by assembly, then this C variable needs to be a global variable. Let's recall what kind of variables are global. First of all, any variables that define out of main, that's global, because main is the top layer of the scope. Remember, C, we basically talk about scopes. And the other one is external variables are global, and they are global, and they are accessible from all the C files and the routines. If you define it as in the out of the main layer, but that one does not have a storage file, right? Remember, it's basically just a symbolic link to some storage base. And also, for assembly to use this to avoid because in assembly there's no type checking or name checking. Remember, the assembly, the compiler, one convenience compiler gives you is it always enforces the type and enforces the name. So if it sees multiple names, it will basically automatically give you a compilation error, and your program will not even hit the microcontroller because it already will have compilation error, right? But the assembly does not. So assembly, if you happen to define some variable that has the same name as the C language, that will not be automatically detected because you could be just giving a shortcut name for a register. But in the C language, you define the integer with the same type, the same name, right? So that's going to be, let's say you rename your register 16 to be 10. And in the C language source file, you basically also define an int that's called 10. If you don't define as the external modifier, then it will compile okay, actually. But what you really mean is basically this temp and the other temp should be the same thing. Otherwise, you should give it a different name. So that's basically a typo for you. So it happens to give two identical names to different variables. In this case, the compiler and assembler will not be able to check this unless you actually put an external modifier in the assembly language. Then the assembly language will say, for this variable that I define here, I should also check the C source files and see if they're same name variables. If there is, then I should basically copy whatever the storage definition for that variable over, and then I will be referred to that, right? So if the list files say the temp variable is actually stored at memory 500, and that's the memory location for that. Then the assembler will copy exact the same thing over and to facilitate its own processing. So that's going to generate a consolidated list file. If you're interested, you can actually play with it, and you will see these two are basically consolidated.
So are we trying to like mix assembly language with the C language in the same file?
No, it's not in the same file. It's in different file.
They're in different files.
Yeah, in different files.
And if I actually, let's say I rename the register R15 to 10, and C I use int 10 is equal to 10.
Right.
So what happens?
If you don't add the external modifier, then the C, if you haven't defined the temp variable in C, that's going to give you a compilation error. So that variable is not defined. If you define the temp variable, then that temp variable is going to be another storage. That's not going to be your R16.
Okay.
Yeah, which you actually meant R16, but you thought that's going to be the same variable as not. Because without extern, the assembler will actually not check the name conflict in two source files. Because the reason is because any variable name is just for convenience, right? At the end of the assembly process or compilation process, there's no variable name anymore, right? Everything is mapped to some location. So that's why if you don't add extern, so on this side, yeah, the assembler will pre-process this into your R16 become R16, right? The temp become R16. And in the other C language processing, before it even hits assembler, it will automatically allocate the storage location for that temp variable, which is some memory or register. It really depends on how you define that. If you define as volatile, it's probably a register. If you define as register, it's definitely going to be register, right? But if you don't define, it's somewhere in the main memory. And then the two assembly file will be coming together, and one is say this memory is here, and then say register is here. There's no way that they can link both up. So that's why you add extern. So that's going to add a certain stage, the intermediate stage. Say, okay, when the C compiler compiles this, and before it generates the final assembly, and the assembler actually to generate the assembly code, they are going to cross-check and see, okay, are there any variables that actually has the same name, and the user actually meant that. So it's not user type, user actually won't do this. So did that answer your question? Okay, that's basically the extract. So why we don't have we don't use global variable in assembly, and then we use external modifier in the C when we access assembly variables? There's basically two reasons. First one is the global really doesn't make any sense in assembly, because in assembly everything is global, right? So there's no need that you say this variable is global with or without the global modifier. It doesn't matter. The other thing is for the C compiler, the extern also has a meaning, because the extern that's at the compilation stage, the extern also has the use that they use to look at other C files. So that extern is basically reserved, because we talk about the assembly extern is used when you are merging two assemblies language, two assembly files. But the C extern will actually happen at the compilation stage. So that one is already pre-processed there. That's why when you are when you are trying to access a variable defined in the assembly language by the C language, then you basically don't need the global and the external modifier. That's basically that. Okay, so that's basically the variable visibility. So after this, then we will understand that in our source code, eventually the variables defined in one file, source file, will be usable in another source file as long as you define it properly. Right? So the other thing is that's in the variable data part of it. So what about the program execution part of it? So for that one, we are mainly talking about functions, because you don't go to another piece of code unless you are using some jump, BRNE, just branch, right? All this kind of thing, and even all these ones actually are mapped to either control flow right? If else, while, do while, or function call, right? And function call is most popular in this case. So when you do and the control flow really doesn't matter, because when you are saying when jump to something, you are actually jump to a label, and that label itself could be resolved by the variable visibility, as we talked about earlier, right? But for function, it's a different thing. Yes, go ahead.
So what's the difference between variable and register? Like we define any variable in our code.
Variable and register. Oh no. So we need to first think about the variable is the naming thing, and the register is the storage thing, right? So we talk about in the memory we have general register, we have I/O registers, and we have general memory, right? So the register is basically the storage place, and the variable is actually in C language is basically used to symbolize a storage location into a name. That storage location could be in the memory, could be in the I/O, could be in the.
It won't be your general purpose register, right?
Not unless you use register modifier.
Okay.
Before if you say register int I, then that I is going to be allocated in the register.
Okay.
Of course, that's the compiler will try best to satisfy your need, but because you define like 33 places, 33 variables, you say all use register, then the compiler is going to do something that you don't see, but it will either discard your request for the last one, for anyone beyond 32, or it might do something that adds some wrapper code, say, each time I use this, I'm going to swap some register variable out. I'm going to swap your register variable in and try best to satisfy it. So that's upon the register, the compiler to do.
So can you give me an example where we can use registers instead? I mean, we can use variable instead of registers.
No. The variable could be mapped to a register.
Okay.
Right. So the reason to use variable is not you say use memory or register or not. It's basically for humans it's easier, because I say instead of memory location 500, now I can say variable name number of students, and then the compiler will automatically put this in some memory location. I don't even need to know where does it put.
So like in assembly language we have whatever bit registers we have, we can use only those registers to move the data around.
You can use register. You can also use memory location, right?
Okay.
Yeah. So you use the registers as the intermediate storage location most of the time, either to do some operation like add or subtract. Then you basically put them in register first. Of course, eventually, every operand is loaded to some general purpose register for calculation, and then you store back. So that variable, but again, this is a storage thing. This is not a naming thing, right? So I think I get the point. I hit the point. I hope that made you clear. But a variable is basically just a shorthand annotation of any memory location, be it a register or general purpose memory location, and you just give it an alias. So when you use it, you can just use this alias to specify for it. For example, I say have home. Instead of give a street address, and then you could actually move to another home. It doesn't matter, because as long as I say your home, or in your phone contact book, each time you see just the name of this person rather than the exact number of this person, because you can always change the banding, and as long as you say I'm calling this person in my phone, it will automatically call his number. So that's basically the variable. Why we use variable, but it is stored. Then you can think as this way. On your phone, it could be stored on your SIM card or in the phone, right? That's like register and general memory. So that's where it is stored.
So when you define any variable, compiler will decide where to store it.
Yes, compiler will decide where to store it. And most of the time, this one is stored in the general purpose memory.
Okay.
because because the general purpose register is precious. We only have 32 of them.
Yeah.
But if you specify your preference, you say I prefer this variable to be in the register. If you use the register modifier, and then the compiler will try best. It's not guaranteed because, as I mentioned, you could be specifying too much. You could be specifying 500 of these variables. They all use register, but it will try best to put it in the register.
Yeah. So basically, register is a place where we keep some sort of constant or by default values of the product or of any.
No. Actually, for these variables, for these ones, in the C language case, you don't even need the storage for them. You just define a constant, and then the compiler will automatically map this into the machine code. Instead of, remember, we used to say, okay, I store the constant number 5 in some memory location. Then each time I always do a LDI, I first take that out. Not LDI, actually. I need to do a move to move that into some register, and then I use that constant to do some add, subtraction, all this kind of thing, right? But in the C language case, you can just say, I define a constant, which is 5, and then the compiler will come in and say, okay, because this variable name is already 5, why I'm storing it anywhere? I don't need to. Any place you use this variable, it automatically replaces it with 5, right? So that's the benefit of a C language. Otherwise, you need to, in your assembly, when you write assembly, you pretty much need to store it somewhere and then take it out.
That's what my question was. That in assembly language we usually have 32 registers and we have to use that to move the data around. But in C language we can use registers as well. We can define it as some name, like define R16 as some name, and we can use that as a constant or by default value because it's like stored in that. The value has been stored already.
True. You can do that, but you are still doing. You can do that. That's completely valid in C language, but you are not taking advantage of the C language, because the whole idea of C language is you don't need to understand where are these storage are, right?
Yeah.
So you just say, I just need to use a variable. I don't care where this variable is stored.
So we don't need to worry about register at all in this.
Yeah, you should not.
I'm just trying to.
You should not need to know the general purpose register, because all these registers, as you mentioned, they're mostly to facilitate you to move data, right? You are using them as intermediate registers somehow. However, all these control registers, their names become reserved variable names. You cannot use it for other variables. So you still need to remember that these names and then use them, right? So for that sense, you do need to understand what is that name for. For example, I say timer TCCB0. Then you need to understand that is basically something that controls the timer, right? Rather than number of students in this class. Right? Okay. So did that answer the question? Okay, sort of. Anyway, we can explain more during the break if you still have confusion. Okay, so let's get back and say, okay, when we need to do jumping around, right? In the code locations in the locations that's generated by different source codes, then how do we know that where to jump to? So for the assembly to see C functions, because C function, if you have, we actually have went through some simple C function, right? F get C, print F, as part of demonstration in the second class, and you will see the C function. Actually, it has some prefix added when it's assembled into assembly. It has some prefix, and also it has some. Instead of just a simple RET, it actually has some cleanup code actually before the RET, right? So if that does not refresh your memory, you can basically do another sample project in your Atma Studio and just assemble, just compile it and look at the list file. So that because of this, then the C function, especially in the assembly to use the C function, you need to pay some attention, right? So luckily, the assembler, the AVR GCC assembler will actually, if you with proper directives, it will understand and check this. So the way to do this is if the C function that you are going to use, then you should give a dot extend modifier, and then when in your assembly, let's see, what is the assembly statement instruction that you use to call a routine? It's rcall, right? Not rjump.
Yeah, right.
It's rcall. So what is the difference between rjump and rcall?
You can return to the one.
It's a relative jump, so you don't really have a return call at the end of, like, once you jump there, it's not going to come back to the
Right.
original place where
So
you
that's
started.
basically the push of the protocol, not protocol, the program counter into the stack. That's the difference of it, right? So that's the same thing. So because in your C function, it's that C function entry actually does more than just push the program counter. That's why with the dot extend and your assembly look at the routines that defined with the dot extend, that it's not going just to do R call. It's going to copy exactly what the C assembler, the C compiler is used for the function entry. It's going to copy that piece over, and it's going to do the exact same thing. So as if your function is called from the C source file. So that's basically how the extern is used. So any questions? Okay. However, when you are doing C code, C code function. Oh, on the C source file side, you don't need to do anything. Why? Because in C code, that unless you use a static prefix, all these function names are always able to be seen. They are always global, so you don't need to define them as global. Okay, so that's basically that's the assembly to call C functions. And in the let me do a small quiz. Just give me a scenario that you actually need to call the C routine from assembly language.
Could do like a print statement, which is pretty extensive. So you might want to call that. The assembly is huge.
No, but you are writing assembly program, but you want to use some ready-made. Yeah, okay, that's one scenario. So another scenario that I can think of is you can use this as a glue. You can actually use some code vision AVR. You use code vision AVR to write the main C program. And in this case, you need to call the AVR GCC generated library from your code vision AVR source file. And this is the difficulty, right? Because both of them are C languages. If you just use source code to compile together, there's no way, because each one needs to be compiled to use a different toolchain. In this case, you can pre-compile the code vision AVR and the AVR GCC C library, C source file into a library, and you write a small wrapper using assembly. In this case, you always write a small assembly code, say dot extern, and then you just use whatever name that's in the AVR GCC, and you call it, right? You just call it, and then in your code vision AVR, that you do another thing. Then you use that to use the .asm, because so far we're not talking about how do you do this cross calling from code vision AVR, right? That's basically the .asm modifier, and then you just call your assembly code, and then that will be indirectly calling the AVR GCC code. So that helps you to basically write routines in both C language, but you can still glue them together into a executable. Yeah. Okay, so these are the two scenarios. But you can think about two more scenarios that could be useful. And for the C language to see assembly functions, then that's much easier, because all the assembly language, all they are expecting. Remember, in the assembly routine, there's already a RET built in, and the RET is doing the very simple stuff just by popping up the program counter, right? That's all it does. So to do this, in assembly code, you need to define that routine as .global. And in the C code, you need to do it as extern. So just as extern function, and that will do. There are some exceptions. That's basically, the exception is for main and ISR. So if you have already started project 1, then you should have noticed that in the AVR TCC, the ISR definition is basically by using ISR plus some number, right? Have you actually started with that? Or you are using code V AVR TCC, I know. Code V AVR, so you probably don't know that. How do you define an interrupt handler in C language?
You have to define interrupt, then your interrupt name,
Yeah,
and your function.
that's the code V AVR, right? What about AVR GCC? Have you worked on that? Not okay. Well,
ISR, then the interrupt vector.
yes.
Number.
So you basically just give a number, right? So the main and ISR functions, they are special case. Because these ones, you don't need to, so the whole reason we use this modifier is because when these two, compiler and assembler start to process the source file, they need to understand that this one is going to be used elsewhere, right? Because it could be, it's possible that it is not going to be used elsewhere. So in this case, you don't need to bother the process. However, main and interrupt routine, once it's defined, it's always going to be used somewhere, and it's always going to be used across the whole final generated hex file, right? There's going to be only one. So there's no confusion, there's no ambiguity. So that's why either the assembly or the assembler or the compiler, whenever it hits a symbol like this, main or ISR1, ISR2, then you don't need to any modifier for that. So you just use it as is. It's going to come back. The only thing you need to add is in assembly, just add a global for that. That's all you need. And C do not need to use the magic turn. Compiler will automatically choose this. Okay, so we now resolve this one and say, okay, the variables and the functions will be visible on each side. And remember, in assembly, we have another thing. We talk about in assembly language, every memory location, every storage location is basically accessible. So when I'm using, I'm combining my generated machine code with someone else's machine code, how will I know that one is not going to trespassing some of my predefined, pre-stored values? For example, I just formed the habit of each time I always put some value in the register 6, right? How could I know that the other file is not modifying my register 6? Well, I'm just using C to program. That's easy. Because, see, first of all, we have a scope, right? So if I have two functions, and the variables defined with the scope, within the scope of each function, they are not going to interfere with each other. The second, if I'm going to modify some variable out of my scope, I will not be able to do it, right? For example, I have a function, and I have another function. This function is, I just would like to secretly modify the variable in another function. That will not happen because compiler will tell me that, hey, you are accessing a variable that's out of your scope, right? But in assembly, that's not the case. For example, if I write it very carefully, I could write a library that I say, this is a nice printf. It's going to give you very nice printf functionality. Welcome to use. And Mike just downloaded this, then my C library, and they start to use it. But my library actually have a very secret case of functionality. It will actually modify the timer 1 interrupt routine entry. Instead of pointing to whatever the user defined, I just pointing to some other routine defined by myself, right? And in this entry, the timer entry, I add an offset. So in this case, I'm effectively add a skew to the existing timer interrupt, whatever that timer interrupt is. I add an offset to that, right? And that could create something that's harmful. And it all depends on what kind of system you are attacking, right? For example, you work for the military, right?
Mm-hmm.
Yeah. So for example, I don't know, but I just make this hacking, library. It looks like a printf, but within it will always add some random offset to the timer 1 interrupt routine. So that timer interrupt routine is going to be either delayed or shortened a little bit, right? And then Mike just downloads this and use this to program, let's say, some missile, right? And the missile goes out. And while the missile is periodically using a timer 1 interrupt to survey the ground location, to locate itself, the timer is off, right? So the missile use that to calculate its own speed is off. The missile eventually hits something. Although I don't know where the missile is going to hit ahead or behind my destination target, of course I know it's not going to hit my target, right? Of course, if that's a by design missile, if you ask it to hit point A, it actually hit point B, then you may actually accidentally hit yourself by adding the interference. But anyway, by this kind of thing, then that one is not good, right? So the C compiler will actually prohibit you from doing that, but assembly will not. So that's why the reason. So because of that, then we need to trust that when we are writing, when we're putting some values in some registers, we need to trust that the compiler will help us to enforce some rule that help to protect. Of course, this protect will not be as fine as defined as in the C language itself, but without at least we can protect some of our registers. So that's basically the parameter passing part. So let's do it. Let's have a break and then continue at 9:10. Not 9:10, 7:10. Okay, so we talk about the three aspects of that. We talk about how do we see the variables. We don't talk about how do we see the functions, and we talk about how do we call the functions. And then the next item is basically say what kind of expectation we should have when we, what kind of least insurance that we should have, peace of mind that when we are calling cross-calling functions, what kind of storage location will stay intact, or for sure it's going to be changed. So in this case, we can take some countermeasure to protect them actually before we start to bring in some alien code, right? So that's basically the idea of this. So the register usage when we are using the AVR GCC toolchain, remember this is just for the AVR GCC toolchain. Each toolchain has its own way of doing things. And if you make the same assumption for code being AVR toolchain, it may be completely different, right? It's also very reasonable. Let's say if you use some customized compiler, but in the Atmel, it's not the case because Atmel always use GCC based. But if you are, for example, you're using a Snapdragon processor, and then you just assume that some ARM compiler you downloaded is going to manipulate the Snapdragon register the same way that you have been doing, then that's completely wrong. You always need to read the tool menu, right? Not the datasheet of the hardware, but you need to also always look at the toolchain menu and see how the toolchain makes its own arrangements with regard to high-level language to low-level language mapping. So the details of this can also be found from the application note 1886, and but it's in overall it's like this. So register 0 is a compiler will always use register 0 as a temporary register. So for example, if you will need to move data around and you need an intermediate temporary register, then the compiler will always choose register 0 as the first choice. As the first choice, of course. If you are moving 2, then that's another matter, right? So for example, these are the examples that I added. So for example, in your C code, you put port B equal to 5. And remember, in the port B equal to 5 case, we are moving a constant to IO register that we cannot, there's no instruction can do this directly. Remember, the IO register will only need we will only use out and in, and so anything with constant you need to do LDI, right? So in this case, although in the C code you're only seeing port B on the left and 5 on the right, when it's mapped to assembly, it always needs 3 parties involved, right? There's some 3 middle guy, and there's destination. So the way to do this is that middle guy is always chosen as R0 as the first choice. So that's going to map to LDI 5 into R0, and then we will out R0 value to port B. So the second arrangement is R1 will always be cleared out by the compiler. For example, you say OCR 1A that U equals to the value of R6. So in this case, the OCR 1A is basically 2 8-bit register, right? It has a high byte and it has a low byte. In this case, it needs to populate something into the high byte. That actually happens very often. For example, that's when you're using XYZ register, and in this case, you are moving something around, then you are using XYZ register as to store some value of 8-bit value. In this case, you always need to populate 0 to the high level register, high byte register. So in this case, you need a 0 value, and instead of doing a LDI 0 into R0, you can basically just pre-store 0 into R1. That's what the compiler does, and then it uses this to a 0 value. So that one is mapped to, first you move the value of R1 to OCR1A higher byte, and then you just move the value of R6 into the lower byte. That's basically how this is. And the compiler will do as a courtesy to save some of the registers automatically for you. That's basically R2 through R17 and R28 and R29. So the way there's a gap is because from R18 to R27, they are used for parameter passing, and that we are going to see very soon. So
for example purpose detailing, or is it
by default, the compiler will do this. By default, the compiler will always save this value for you. I'm just so this example and the previous example are just the compiler. The principle is to do this, but how exactly it does this? You need to look at the list file, right? So I'm just giving you. If I'm writing the compiler, I'm going to do this. Basically, you have a spec, right? The spec says this one needs to be saved, and the way you can do this. Of course, there are other ways to do this, right? You can actually remove each one of them into an intermediate register, and then just push that register into a stack, right? And you just keep pushing the same register, and then you pop one register, and then you move that register into another register, and then you pop again, and then you move again. And in this case, I'm pushing one by one. I'm popping one by one, right? But there's many ways to do this. For example, you have a C function that's called do nothing, and this one really does nothing. There's just a no instruction, and it could be compiled like this. But first of all these registers are pushed in, and upon return, all this one will be popped out. In this case, that in your assembly code, that's going to be called by this. You actually assembly code is calling this. If your assembly code is using some of this register, you should feel safe, because this compiler will actually enforce this rule for you. No matter what the user have done in the do nothing function body, it doesn't matter, because before the function was ever executed, all these registers are already saved. Of course, saving register itself is an expensive operation, so that's why we're not saving many of them. We're just saving 16 plus 2, 18 of them, right? That's already a big overhead. That's why when you are seeing printf, you see like 900 lines. Among them, there are 36 lines that this is already to save these registers, right? Because there are 18 of them. Okay, so and other ones R18 through R27, R30, and R31. And just recall, what is R30 and R31?
Z.
That's the Z register, right? And so the reason to do this is because in your C language source, C source code, you always need to do some memory access, right? So you always need to use some indirect register. So that's why this pair of this register is basically used. It's going to be ruined anyway. So instead of saving it, saving it is expensive. You say, okay, well, I'm going to save the first two pair of the X and Y registers, but for Z register, let's assume in your assembly language you're not going to use that many indirect registers. So it's going to be for sure, not for sure, but it's not guaranteed that it will stay intact. I say don't expect it will stay intact, although we may not change it, but don't expect it. So that's basically the table. If you look at the application notes, that you will find the table. That's basically the cheat sheet you need to use. When you are designing some project, you always need to verify. Okay, and that just solved half of the problem, right? Half of the problem says, well, I'm using cross-language function call that we have the assumption of how the registers are going to be changed or not changed. But the other thing is, when I pass in parameters, where are these parameters going to be stored? Especially for assembly, this is very important. For example, I have a C language routine, which I'm taking 5 parameters. So the assembly caller needs to prepare these 5 parameters first, right? Then you prepare, you put them in, and then you start to call the C routine. Then the C routine will be taken the parameters out. So you need to understand where are these parameters actually stored. So the rule is like this. So if our parameters are not that many, then the register 25 through register 8 will be used for parameter passing. And the way to do this is it will start from register 24 and 25, because each parameter will at least take 2 8-bit locations. So to do this is, and so in the C source file, from left to right, it's going to be mapped for this register pairs one by one. So for example, your do nothing function actually takes 2 parameters, and each of them I purposely define them as 8 bits. It's a character variable. However, in this case, because the minimum storage for each parameter is going to be 2 registers, 16 bits, then that's going to be prefilled with 0 and then get called. So in this case, the value of parameter A is going to be stored in register 24 and 24, and 25 is going to be filled with 0. Likewise, the value of parameter B is going to be put into register 22, and 23 is kept with 0. So any questions so far?
What about for anything larger than 2 bytes?
Yes, good question. So for anything larger, for example, you have a structure. Your structure in that, you basically put an integer and another integer, right? So in this case, this with the 2 byte thing, that's going to be put in a chunk that's the multiples of 2 bytes. For example, that data structure actually takes 8 bytes, then it's going to be 20, 24, 25, 22, 23, 20, 21, and 18 and 19, right? So these ones are going to be taken for your structure, which is holding 2 integers. So what if I look at this? So register 8 through register 25, that's 18 registers. 18 register will be able to take 9 parameters at most, assuming every parameter is not exceeding 16 bits, right? 9 at most. Not to mention if we have some big parameters that Matt just mentioned, this one parameter could be taking 8 bytes, 8 bits. So what should I do? In this case, if you exceed that storage area, then that's going to other value is going to be put in the stack, right? So in this case, if I have my assembly is going to call a C routine, and I'm going to pass a lot, and then I will prepare all the parameters in the register first, and when route registers, I will put in the stack. The way I put in the stack is how to do it. Even if I know the stack pointer, I should not be directly moving data into the memory location, right? I should always use push command, push instruction, because the assumption is in the C routine, it's going to use POC to retrieve this, right? So that's basically what I should do. And what about return values? So return value is also if the same register 25 through register 18 will be used if there's still space. That's for return value hosting. The good thing for a C routine is when the C routine is being compiled, the compiler already knows how many parameters it will take, what is the size of parameter, and what is the return. So it can actually sort this one by one, right? So for example, I have a version 2 of the do nothing routine, and it will return some integer value, right? So in this case, because my parameters are only using 4 registers, then starting from the 5th and 6th register, I could use it for the return value, right? So that's basically what I do. And in this case, what about the unused, but it's going to be, that's not guaranteed that will stay intact registers, that become uncertain behavior, right? But that you should not assume that anything happened to that. For example, the compiler, for example, this evening, some engineer at AdMail may just say, hey, what if I'm going to, for any unused register, because for safety, security concern, I'm just going to clear out whatever data in there. So he may make this change and submit the change. Tomorrow release, we are actually reflecting this. But you made the assumption, you say, because these ones are not used, so it's safe. Then your assumption is broken and your code starts to behave weirdly, okay? So you should not make any assumption for this case, in this case. Okay, so we finished the application node explanation. And the questions so far? It's all good. Okay, now let's talk about if you have already get this EEPROM, or you're going to get this EEPROM. This is that gadget is fun to play with. Let me just briefly talk about what is the characteristics of this EEPROM chip. This chip actually, it stores data in 8-bit unit. So that has 32K units on this chip. So that makes total 256 kilobits, that information that you could store. And it has 8 pins. It has power supply, ground, and the VCC. And then it also has chip select. So the chip select is basically in your hardware diagram, by putting the chip select pins high or low, you create a static configuration. In this case, you created a part of the address that's configured by the hardware, because this chip, when it's shipped out, then you cannot say, okay, I buy a chip with the address being 7 and give me another chip being 5. So it needs to print this address on the chip, right? Instead of doing that, it say, okay, we just give you something that has 3 bits that you could define by yourself, that's in hardware, right? By putting high or low. So by doing this, you will configure the address of it. So that's basically, there are 3 bits that you can match. By doing this, you can actually put the 8 of this chip, each one with a unique address on the SQLC bus. That's basically what you can do. And the data and the clock line, that's these ones you need external pull up for them. And the write protection line, once you pull this high, then basically that EEPROM chip is protected. Then you cannot, it become read only. It's like a ROM for that. Or if you put it low, then that's read, write, okay. So this one cannot work as the master. That makes sense because this one is actually not reading any data out, right? It's always as the passive storage. So it's always a slave device. And remember, in the I2C case, who controls the clock? Master. But the slave can also do a certain degree of freedom. What is that? Yeah. It can basically hold the clock line low. In this case, it refuses to do any bus transaction, right? Okay. Unlike SPY. So in the SPY case, who controls the clock?
Master.
Yeah, it's only master. So that's basically the only difference. Not the only difference. One of the important difference between SPY and I2C because each of them are actually a two-wire protocol. Okay. So the way to address this chip is before we will send a start I2C signal. What is the I2C start signal? Pull the clock high, and then pull the data from low to high. That's basically the start signal. What is the stop signal? Keep the clock high and has a falling edge on the data line. That's the stop signal. So the way is that after start, then that's going to send a control byte. This control byte, the first 4 bits is always prefixed with 1010, and the next 3 bits are chip select bits. That's basically mapped to one of the 8 addresses. And remember, in the I2C case, that control byte is pretty much an address byte, right? But because the address byte, we only need to 3 bits. In this case, for this chip only, right? Because for this, you may have on the same I2C bus, you have 20 other chips. But these chips are not going to be prefixed with 1010. The 1010 is kind of like a vendor ID, vendor plus model ID for this chip. Let's say this is a chip manufactured by some vendor, and this is the model. So that will not that's going to not going to mix with other I2C devices, hopefully. So but however, in the I2C address protocol, it always says the last bit determines whether if it's a read or it's a write, right? So the 1 is for read and 0 is for write. So for the certain chip with a certain address configured, that means there's a certain combination for the 3 address bits, that you still have 1 bit that you can say this data is going to be write to the chip or it's going to be read out from the chip. And then after that, you need to say which unit I'm going to address on that chip, right? So for that one, you need to send 2 address bytes. This one is basically the memory location, and higher, that's the thing is the higher byte first and the lower byte second. Because we only have 32K, then we are just using 15 bits of the address bits. The first bit is always reserved as 0. I'll send this in. So to do this in assembly, of course, I mean this warm-up exercise, not this do-it-yourself homework. I'm not going to grade it, but you can try to do this to make your own library. Is we first need to understand at the assembly level how are we going to manipulate the I2C bus, right? So the I2C bus is we need to first send a start, and then we need to send a control byte, and then we need to send the internal memory address, and then we need to send the memory data, and then when we send a stop. In this case, I fulfill one write transaction over the I2C bus. And that's actually the read, operation. The write operation is pretty much the same. The only thing is in the control byte, the last bit is last bit is 0. So 1 is for read and 0 is for write. So that's the only difference. So that's going to work this way. So okay, so in this exercise, I ask you to write the assembly routine with these names, and then after this, you use the build as a library option in your assembler. Then you can build a library, and then you can use it in your C language to manipulate this specific chip, right? So the example I give you is you can say I2C get bus, and I2C start, I2C read, I2C write, and I2C stop. And after that, when you are doing when you put a EEPROM chip with chip select to be all zeros, then in your C source file, you can basically operate this using these assembly routines. You can do get bus, start, write, and read, and then stop, and then return the value. And for the write, it's similar. Okay, so why you would think, hey, this is not some simple task, and why are you defining some helper functions such as get bus? Okay, the trick is I map this exactly one-to-one to the internal implementation of the code vision AVR. So if you use the code vision AVR, and then you use that to generate, to use code vision AVR C source file to generate the I2C read and write, and then you compile this, then you will see in assembly, it will already contain all these helper functions, and then the C function call is going to be mapped into this one. Okay, so that's also a good exercise for you to look at code vision AVR. So for code vision AVR, the good thing is for any functionality that you are not familiar with how it is going to be implemented in assembly, then you just use the code vision AVR C library, and then you just compile it, and then you look at that's pretty convenient because it offers more ready-made library than AVR GCC. Okay. So that's basically it for today's class. And any further questions?
Are we going to be using that then for the final one, the micro mouse one?
No, the micro mouse one is just serial port.
Okay.
Yeah. But this one is for you to basically practice. And this one is useful because if you go to SparkFun, you can buy all sorts of I2C, fancy I2C chips, right? For example, LED, more stepping motor. Pretty much every sensor these days they support I2C interface. So then you always need to write a wrapper, which is kind of like a minimal driver for this to be used in your C code, right? So this is because of the 24LC256, it's such a simple device. You can use this to verify your I2C library, and then later you can use it to bring up some other hardware. So this is basically for you to practice. Yeah. So any other questions? No? It's good. So for the next class, we are going to release homework 2, to just give you a heads up. And also, you're supposed to wrap up project 1 by next week. Yeah. The whole reason we set up schedule is to help you to control your time. Okay. So yes.
Is it possible for you to release homework 2 now?
So why?
I just want to see it so that I can prepare for it.
Okay, I just don't want to interfere with your other stuff. I can send that to you. Yeah. Okay. Okay. Any other questions, requests? No? Okay. So that wraps up the instruction day, and I will see you next week.